Hello, we are coming to you from Cambridge in the United Kingdom to bring you another exclusive electro-optics webcast. This time, the topic is photonics advancements in aerospace and defence, and it's a subject that we know has a lot of interest with our audience. And so a big welcome to all of you who are joining us online now, and indeed all of you who are watching us on demand later. My name is Mark Elliott, and I'm delighted to introduce our speakers today. All have unique perspectives on a really interesting subject, which is obviously incredibly topical at the moment. We have, in alphabetical order, Jason Ball, who is a technical marketing engineer from Liquid Instruments. We have Jian, who is the Chief Product Officer and the Deputy CEO of Cailabs, and is also a Photonics 100 honoree, so congratulations, Pooh, for that. And also Kenny McCormick, who is the Head of Capability Advanced Targeting from Leonardo. So a very big warm welcome to all of you, and a thanking you for joining us today. We know that efficiency and adaptability is a common objective and is critical, really, to all modern photonics applications. And nowhere is this truer or perhaps more important than in the aerospace and defense industries. When we were putting this topic together, we were interested in how companies are responding to the challenge, what they're working on, and we know there's a wealth of innovation out there that is pushing capability to new heights. So we're really keen to hear what's going on, what the challenges are, and what's being developed to overcome them. Just before we start, a brief housekeeping note, if I may. We are, of course, happy to take questions. We welcome them, in fact. Pop them into the discussion chat that you can see at the bottom of your screen, and we'll try and cover as many of them as we can at the end of the three presentations. So, without further ado, if we could first go to Pooh from Cailabs.
Thank you for the kind introduction, and thanks for inviting me for this webinar. So let me share my screen. Okay, can you just confirm that this is visible?
Yes, that's coming through fine. Thank you.
Great. So yes, so thanks again. So I'm Pooh from Cailabs, and I'm delighted to start this webinar from Cailabs' perspective on how photonics can be used for aerospace and defense, and our own perspective on how important it is for aerospace and defense to master beam combination, beam quality, and beam shape in photonics applications. So just to start, a few words about Cailabs. We are a almost 11 years old company based in France, and our focus really is in mastering and shaping light since 2013. So this is really the core of the company, is how to shape and master the shape of the light for multiple applications. And in particular, we targets really three applications. So the first one is the topic of today, aerospace and defense, and especially for laser communications and optronics applications. The second one is industrial laser processing, such as laser welding, additive manufacturing. And the last one is telecom fiber networks, so local area networks or long-haul fiber networks. So let's start directly into the topic of today, so aerospace and defense. Well, as you all know, photonics is ubiquitous in this kind of applications, and laser light is useful for a large range of applications, so communications, sensing, ranging, countermeasure, directed energy weapon, etc., etc. And in many cases, these applications require the use of free space laser beams. And there are unique challenges that are related to the use of free space beams. They require mastering the laser beam at multiple stages. At the emission of the beam, you need very high power emission in many cases with a very high beam quality. During the beam propagation, you need to control the quality of the beam over propagation, and this is often related to the shape of the beam. The quality of the beam is related to the shape of the beam. And at the reception, mastering also the quality of reception means you need to optimize this reception, optimize the signal to noise ratio of the reception, and this is also related to the shape of the beam. And what we do at Cailabs is that we have our own technology called MPLC, multiplane light conversion, that can help with this different stage of light propagation in all these applications. And I'm going to go in details on how this works. So what exactly is multiplane light conversion? This is a very versatile technology for controlling laser beam shape. It's a technology that's derived from initially quantum optics. It was invented for trying to make quantum computing with laser shapes at the French academic lab called the Cailabs lab. And the idea is that you can do very complex beam shaping through a succession of spatial phase profiles. So by using a kind of textured lens or textured mirror and propagation, and then another textured lens and propagation, textured lens propagation, you can actually achieve almost any freeform shaping. And you can do that over a single beam, or you can do that over multiple beams at the same time. So this is basically a passive optical beam shaping technology, and this has no intrinsic logs, no moving parts, so a lot of advantages for many applications. It can work for any wavelength. We've tested it from UV to mid-infrared at 4 or 5 microns, and it can handle very high power because it can be implemented in a reflective way, up to 16 kilowatts. This is the highest we have tested. And what I'm going to focus on is how effectively controlling the beam emission, beam quality by combining beams. This can be useful for 3 different applications I'm going to focus on. The first one is directed energy weapon. The second is infrared countermeasure. And the last one is laser communications. So let's start with a directed energy weapon. I believe one of the other presenters is going to go much more in details into this, but I'm going to give a few details about our perspective on directed energy weapon. So first of it, what is it? It's basically a weapon without a projectile. So the idea is that it's a weapon that damages the targets with a very highly focused energy. The growing presence of drones in battlefields prove that it has a lot of value in the field, and because there are a lot of new laser sources with very high power and very good beam quality, typically solid-state fiber lasers, this gives a lot of credibility of using this type of weapons with lasers as the source of energy. However, there are many challenges of laser directed energy weapon. And the main limitations that are encountered today are the power, the capacity, and the efficiency of these laser sources. They require military applications for example, destroying drones at distance, require very intense light sources. We're talking about kilowatts and multiple kilowatts, tens or even hundreds of kilowatts in sometimes hard to reach wavelengths. So at 1 micron, 2 microns wavelengths. And so the laser sources on the market are not necessarily useful directly for this kind of applications. They might be very large in terms of form factor. So there's a problem of capacity. We want to use these weapons on the field, are very large, very bulky laser source would not be adapted to that. The electrical to optical efficiency is not necessarily very good for some of the higher power lasers, and the beam quality may be poor. So we have tens of kilowatts laser sources that are used, for example, for laser processing, but these are multi-mode lasers, and so the beam diverges a lot, and they cannot be focused very intensely on the targets, and so they are not useful for directed energy weapons. So what could be one solution to these problems? The solution could be to do what is called beam combination. So basically take multiple sources and combine them, sources maybe with a lower laser power, or let's say 1 kilowatt or 2 kilowatts, and combine them into a much more powerful laser sources. So these lower source lasers have a very good efficiency, a very good quality, and the idea is to combine them into a cost-effective high power source. So it could induce indeed more power. That's the goal of combination, but also maybe a more compact source. You can maybe deport this multiple laser source to another location and have just a combiner on the field, for example. But however, one issue is still to maintain a very good beam quality in this combination. And what we propose with the MPLC technology is that because it can handle and shape multiple beams at the same time, it can offer a very high quality coherent beam combination. So basically the idea is for several, let's say N, here in the picture it's 4 input beams, we can manage to find, to shape each one of them into an ideal decomposition of a Gaussian beam. So basically, when the 4 beams that you see are in phase, they would give a Gaussian beam when they are interfering constructively. And this can be done for 4 beams, as in this example, but it could also be done for many, many beams at the same time. And you can always, if you can control the phase between all these input beams, you can always achieve a perfect output beam in theory at the output. So perfect Gaussian beam with the best quality, the best propagation performances. And that's the idea of how we can use that. And we've tested it with actually a lot of different cases. And we know that this is a way of achieving a very high power. So what we achieve is a very high power handling first. So we demonstrated that MPLC can handle up to 16 kilowatts with multi-mode sources. With single mode sources, we have tested it to a few hundred of watts, so 100 watts per input, basically. And we have demonstrated that this can achieve very high quality. So we've done tests, for example, with 6 channels at 1550 nanometers on current demonstration. And this we have shown 80% of combination efficiency. So this is actually better than the theoretical efficiency of more standard coherent beam combination, such as tiled aperture coherent combination techniques. So this is, for example, one perspective on how controlling the beam shaping and the beam combination can be useful for defense application. Another one is directional infrared countermeasure. It's kind of the same idea, but with very different sources. So here the idea is not to destroy your targets, but of jamming infrared missile seekers. A lot of the self-directing missiles are equipped with imaging systems that enable them to discriminate a target from decoy. And one way to actually jam these missiles is to disrupt these seekers and basically saturate the camera or damage the camera so that it doesn't find the target. And so same idea, you need power on this to illuminate the seeker to destroy it. And the main challenges are kind of the same, also the capacity, the propagation, but also the wavelength that are used. Indeed, in order to jam these seekers, the spectrum of the optical system has to be at a kind of challenging wavelength, around 4 or 5 micron in the mid-infrared. And you also need something that's very compact that can be integrated into an aircraft, for example, and you have to deal with also the atmospheric propagation. And a very useful laser source for this kind of application are quantum cascade lasers. They are very portable. They can emit light at 4 or 5 microns, but they are limited in power. Usually less than 2 watts of power can be emitted by quantum cascade lasers. They're diverge a lot, and so you need to control the beam shape for far field the propagation, and you have to control it, limit the power if you do not want to go into incoherent light and remain a coherent light laser source. And so the same idea of using beam combination can be useful for this idea. So this time we can also use it in an incoherent way, so not necessarily have the inputs overlap and construct a Gaussian beam because you would need a lot of control over the quantum cascade lasers. That's not necessarily possible. But you can also do an incoherent combination. And this time, the output beam is not going to be Gaussian, but because we can control each of the input beam and how it's shaped, we can actually achieve the lowest m² possible, the best quality at the output still, and find the less divergent possible beam at the output that is multimode. And what we have demonstrated here is a combination of up to 8 quantum cascade lasers with a combination efficiency of 80% and m² below 3.5. So that's basically the highest quality you can achieve for 8 QCLs, and then enabling to achieve more than 10 watt of power for direct for countermeasure applications. Lastly, a few words about how this can also be used for laser communications, the control of the beam shape for laser communications. So laser communications, so free space optical communications, is very promising for satellite communications that for the moment are mostly done with radio frequency, but it has 3 major benefits compared to radio frequency. It's fast. You can achieve very, very high data rates, more than 100 gigs per second. It's secure. It's the probability of detection and interception, it's much lower than RF beams. And it's license-free. You don't need a license for communications. However, the atmospheric turbulence is a very challenging problem for communication through the atmosphere. When you send a perfect Gaussian beam through the atmosphere, it gets disturbed by the laser, by the atmosphere, and at the end, what you receive is a completely distorted beam that's dynamically changing over time, as you can see in the small video. So it's important to correct turbulent beams to cancel the impact of the atmosphere. Laser communication, basically, it's competitive with radio frequency at high throughput, above 10 gigabit per second. And for this, you need to couple into single mode fibers. So you need to use very small detectors with a very good signal to noise ratio. You want to use coherent modulation. You want to use the existing fiber amplifiers that are used for telecommunication, EDF, erbium doped fibers. And so it's important to mitigate the effects of atmospheric turbulence, because if you don't do that, you would have very deep fading and you have very inefficient single mode fiber coupling. On the bottom right, you can see, for example, a graph showing in blue what's the light that could be collected by a telescope on the ground, and in orange what could be actually coupled into a single mode fiber. So you have a lot of losses, but you also have a very strong variation of power that no detector could follow. No dynamic range of detector could follow this like 40 dBs of variations, and so you could not detect the signal properly. And the approach we have is a bit different from the typical approach for turbulence mitigation. For astronomy, the approach is to use what's called adaptive optics. So to measure the wavefront of the beam and to use deformable mirrors to actually correct the effects of the turbulence. And what we do at Cailabs and using the MPOC technology is actually to decompose the turbulent beam into different spatial shapes, different modes. So again, using the shape of the light as a way to analyze the beam and to control the beam, and then recombine these shapes into a single mode fiber. And so we do that with our technology of multiplane light conversion and with Photonics integrated chip for the recombination part. And this can enable turbulence mitigation. So the same graph on the bottom right, now with our technology, so-called Turbo Atmo, then we use 45 spatial modes to actually analyze the turbulent beam, and we recombine this beam, and then we can recover almost all the light that was collected by the telescope, contrary to a direct coupling into a single mode fiber. And all this can be done in a very plug-and-play compact systems compared to what would be done with adaptive optics. So basically, I've covered three applications. What I hope the message you can take home is that basically beam quality and beam shapes control are essential for photonics application in aerospace and defense. I've shown examples in 2 defense application and 1 laser communication application. And that beam shaping technologies such as the MPLC can enable this kind of control by improving the power at emission, so enabling high power source thanks to combination, enabling a very good control over beam propagation thanks to beam shaping, and an optimal detection even through turbulence thanks to spatial beam shape analysis. Thank you for your attention.
Thank you, Pugh. That was really interesting. I was struck by the challenge of the efficiency and indeed the accuracy kind of challenge that is obviously inherent in all photonics, but particularly, I guess, in this area. So I imagine we will come back to that in terms of questions at the end. Okay, thank you very much again. Next, we have Jason from Liquid Instruments. Jason, the floor is yours. Thank you.
Off mute here, and let's do the slideshow. All right, how's this looking for everybody? Is it changing?
Yes, it is. Yeah, that's good.
All right, wonderful. All right, good morning, afternoon, everybody. My name is Jason Ball. I am an engineer at Liquid Instruments, and my topic for today is reconfigurable measurement solutions for aerospace and defense applications. So before we get in, I would just like to give a shout out to Electro for hosting the webinar today, and to our co-presenters at Cailabs and Leonardo. Thanks, you guys. Very interesting stuff you guys have to present today. So really appreciate all the effort and promotion that went into this. So who are we as Liquid Instruments? Well, we're innovator in reconfigurable high-performance test instrumentation. We were founded in 2014. We spun out of Australian National University with technology that was originally developed for gravitational wave detection. And we are developing and commercializing instrument-on-chip technology, which I'll talk a little bit more about in subsequent slides, what exactly that means. Currently, we have offices in Australia, Sweden, California, the latter of which I'm based out of. And at the bottom, you can see some of our users of our products. So the basic philosophy behind our products and our main device, which is called the MOCU, is that we are trying to evolve test and measurement equipment. So I'm a scientist. We know that any optical photonics experimental setup can get quite complicated. You've got all these individual instruments, individual text boxes. You've got instruments like an oscilloscope, an AWG, a waveform generator, spectrum analyzer, etc. Historically, they've all been separate devices, separate interfaces. You've had to, they only, they're fixed function. You've had to manually integrate them, either via physical connections, via software. And this can get a bit unwieldy at times. So there's been a push to kind of make hardware solutions more modular in the past, either through, PXI modules. The idea is you have different hardware modules on a PXI card, which can slot into one of these chassis, and you can swap out hardware as needed. It's easier to integrate all the instruments together, through the backplane, etc. However, you still are limited to the actual physical hardware on the device, even if you've got some more flexibility and some more streamlining in terms of space. So we're taking this idea, we're taking this modular idea a step further, and we're saying, what if the hardware was replaced with something reconfigurable, something flexible like an FPGA, and the software was modular? So we've introduced what's called the MOCU, and you can see we have 3 different MOCU devices here. And it is based on a reconfigurable FPGA with a suite of instruments that you can load onto the memory of the FPGA for whichever application you need at the moment. So the idea is that this can be reconfigurable. It can upgrade, evolve over time. It can meet any changing scope or demands of your experiment, and it can streamline your control and your integration of your lab setup. So what instruments does the MOCU have to offer? Well, we've got your standard, desktop, your standard benchtop instruments, your spectrum analyzer, your oscilloscope, your waveform generator, things like that. We also have more advanced instrumentation, things that are more unique to the MOCU platform, such as the phase meter, which I will talk a little bit more in detail about in the next couple of slides. Things like a laser lockbox. I've highlighted on the left a few instruments that I think may be of interest to the photonics industry, photonics experiments, such as our phase meter, our lock-in amplifier, DC to 600 megahertz dual phase lock-in amplifier, a time and frequency analyzer, which is our newest instrument that we've just added to our platform, which has 4 separate event and interval counters and can generate real-time statistics, performing measurements like time interval analysis, frequency counting, event counting, et cetera, et cetera. And these instruments, all of these instruments can be deployed on the platform through something called multi-instrument mode. So the FPGA on the MOCU doesn't have to be reconfigured to be just one instrument. It can be partitioned and can be partitioned in up to 4 slots. And you can deploy up to 4 instruments or multiple copies of the same instrument simultaneously alongside each other. And I'll show you an example of how this would be used. So just talking a little bit more about multi-instrument mode, you can see me on the right here. This is just a little short video I took of me just kind of messing around with the system building feature of the MOCU. So I'm dropping different instruments into the different slots. You can see as an instrument appears in the slot, there's these black lines which represent the connections between the instruments. So there's different inputs and outputs on the instruments. I'm kind of clicking and dragging those around to change them. And as you can see, you can very quickly switch out instruments, and you can change the connections between the instruments. And then all you have to do is apply the changes, and the FPGA reconfigures in a matter of seconds. So especially if you have more than one instrument in your test setup, this helps you streamline, and the connections themselves are fully they're fully digital. They're within the MOCU itself. So there's no adapters, there's no connectors required between the instruments. You don't get insertion loss or phase shift. That's characteristic of analog components, or cables, or even bad cables. And it reduces your physical footprint, right? So instead of having a separate AWG, oscilloscope, spectrum analyzer, they're all on one single device. It saves you space. And all of these instruments, the control of all these instruments is streamlined as well. It's all done through one single interface, our MOCU app, our software. So you can just launch a few different windows to control each instrument, which all control very similarly. And I'll show you our MOCU UI in the next couple of slides. So as far as using the MOCU product for aerospace and defense applications, obviously there are a huge number of applications that we could see our instruments being used for within this field. I want to focus, in the interest of time, I just want to focus on one in particular, which is the accurate measurement of phase. So, this could go under, precision optics, under, atomic clocks, et cetera. Phased arrays, accurate measurement of phase is a very important thing to be able to do. So Let's talk about our MOCU phase meter. Now, we know that measuring phase precisely is incredibly tricky. Every frequency source, every oscillator has jitter, has frequency drift. There are short and long-term instabilities that are characteristic to any oscillating system. When you're measuring phase, you have things like phase wrapping, which limits your detection range to 0 to 2 pi or minus pi to pi. And if it goes beyond that, it wraps around. So if your phase differences become larger than that, it can be hard to suss that out. So we have deployed on our MOCU platform the phase meter, which is an instrument that is unique to our platform, and it is based on one of the most sensitive measurement systems that's ever been created, which is, for gravitational wave detection, as I said on the earlier slide. So how does the phase meter work? Well, it utilizes something called a phase-locked loop. So I've got a small diagram of a phase-locked loop down at the bottom. So the idea is you have some sort of input signal. This can be either a signal that's internal on the box itself. It could be coming from one of the external ports. It's passed into a dual phase mixer, or an IQ mixer, dual phase demodulation. Can output the XY or R theta. So the idea is that you demodulate it, it outputs the phase, that phase passes through a low-pass filter, and that phase signal is also fed back around into a voltage-controlled oscillator. So the idea is that this acts as a feedback mechanism, and so if there is a deviation from a central frequency that's detected, then the voltage-controlled oscillator will, the voltage going into that can adjust the output frequency such that it matches the input signal. And this way, this is where the locking comes in. So this acts as a feedback loop that locks onto an incoming signal. And you can see that on the right, this is the interface for our phase meter. You can see that there is a single input. And on the right here, I have it set to automatically detect the frequency. And so it's picking up a input of 150 megahertz, and it can measure the frequency information, the amplitude information in dBm, and the phase information. So this is this phase information would, going back to this diagram, would be the output from this integrator here. So basically this is adding up, this is accumulating the error, it's accumulating the deviation from your ideal target frequency. And this is incredibly precise, can measure down to the microcycle. And you can measure phase, amplitude, and frequency information over multiple channels. So 2 channels if you're working in multi-instrument mode, or if you're using the phase meter in standalone mode, you can do up to 4 channels. And in addition to detecting and measuring incoming signals, you can also generate up to 4 phase synchronized outputs. So you can basically make your own phase locked loop. You can output a signal that is a phase locked copy or a harmonic of your input frequency. So just to show you this in the context of the instrument, I've gone back to the MOCU, build your system, the system building screen, and what I've done is I've taken the phase meter instrument, I've put it in slot 2. I've taken the waveform generator and I've put it in slot 1 to kind of mimic, some kind of incoming signal that you might have at one of the input ports. And I've also put an oscilloscope in slot 3. And so this is just a quick demonstration to show, all right, here's a waveform generator. It's got a signal that's being output at its output A. It's being fed into the phase meter. It's also being fed into one of the inputs of the oscilloscope. And then the phase locked output from the phase meter will go into input B of the oscilloscope. So this is how you would set up one of these systems on the MOCU Pro. You drop all of these instruments, you configure the FPGA, and then once all of these instruments are loaded onto the device, you can open up the control windows for each of these instruments, and it would look something like this. So all of these these are all three of the windows for each instrument that I've arranged. All of your instruments are controlled in separate windows. So on the top left, we've got the control screen for the waveform generator, where we can generate just a simple sine wave at 150 megahertz, turn the output on and off, adjust the offset, the frequency, the shape of the wave you're outputting. You guys have already seen the phase meter screen on the right. So this would be automatically detecting and locking onto that 150 megahertz signal. And you could enable, I don't have the tab viewable, but you click on the top right tab and you can turn on the phase locked output. And so then you can view that output in the bottom left here, which is the oscilloscope screen. And so you can see the original signal coming in from the waveform generator, and also the phase locked output from the phase meter right alongside of it. And these two, if you could see this in real time, these would indeed be phase locked together. They'd be fixed in the position on the screen there. So this is how to accurately measure phase and create a phase locked loop with the MOCU phase meter. This is just one of many applications that you could use the MOCU instrument for. So just to recap, our MOCU, it's a reconfigurable FPGA-based device. It offers a suite of instruments for helping your, increasing your flexibility, your streamlining of your experimental setup, and increasing your efficiency. We've got 3 different versions of the MOCU. So the one on the bottom on the right here is called the MOCU Pro. That's our most advanced. It's got the best specs and has 4 inputs and outputs. We also have the MOCU Lab, which was our first product. It has 2 slots and 2 input and output ports. And then we have kind of the budget version for kind of basic benchtop and even into the hobby for hobbyists, called the MOCU Go, which is on the top here, which is 2 slots and also 2 inputs and outputs. We let you deploy up to 4 instruments on the Pro side by side, which can replace a number of individual test boxes in your experimental setup. Not only do we have, your basic benchtop test instruments like a spectrum analyzer and an oscilloscope, we also have unique instruments such as the phase meter, something called the laser lockbox, which I haven't even gotten to, for precision phase measurements, for laser locking, different advanced devices like this. And we also are very flexible in terms of how you can control the MOCU. So we have our own MOCU app, which is what I've been showing you screenshots of, which is available for Windows, Mac OS, iPad OS. We have a Vision OS version of it, which you can see on the right. And we also have Python, MATLAB, and LabVIEW APIs if you prefer to use your own software to control the instruments. So just really quickly, at the end, just some upcoming events. I'll be giving a webinar on our new time and frequency analyzer on May 22nd. And we will be, I will also be, one of our apps engineers will be presenting a webinar on PDH pond driver Hall locking with our box on June 18th. And also, if you're going to be at APS DeMop, or if you're going to be at Optics and Photonics this summer, we will have a booth there. Please come check us out and talk to us if you're interested in learning more about our test and measurement solutions. And with that, I'd like to thank you.
Thank you, Jason. That's a really interesting sort of product set and things. And okay, and last but not least, Kenny from Leonardo is going to talk us through the view from Leonardo UK and the global view of what's going on in the wider sector. Over to you, Kenny.
Good afternoon, everyone. Let me just share my screen with you. And give me a second. And I'll try not to hold you all too much past the hour. So let me know if you can see those slides, everyone.
And yeah.
Yes.
Okay. So quick introduction, so Kenneth McCormick, I'm the head of capability for advanced targeting electro-optics for Leonardo in Edinburgh, specifically working on a number of EO products, which I'll go into in a little bit. So I'll go through this very quickly. Just a lot of people aren't aware of who Leonardo are because we've changed their name so often in the last 15 years. But we're a global aerospace and defence company. We have about 53,000 people worldwide. As you can see, probably getting on for 2/3 in Italy, 15% of that workforce in the UK, and some spread out in the US, Poland, and rest of the world. As you can also see, we have some joint ventures and shareholdings. We wholly own Leonardo DRS pretty much in the US. We also have a 25% share in MBDA and a 22% share in Laramart. Hensoldt, and 60% in Laramart. So a fairly diverse company. Within the UK, we have about 8,100 employees. We generate about 30,000 total jobs across the UK. We have 900 people on apprenticeships or graduate schemes, so we're very much focused on diversifying and pulling through the younger people into our workforce. We have 8 main sites in the UK. I'm based up here in Edinburgh in Scotland, but we have another 7 sites in England, from Newcastle all the way down to Southampton on the south coast. And importantly, we spend about £600 million with the supply chain in the UK. So we like to try and use a vertical integrated supply chain within the UK if possible, and extending to Europe and the US where we need to. Specifically, with regards to Edinburgh, what we do here, so we have a number of key capabilities, world-leading capabilities. So we are, outside of the US, the world leader on fire control radars. We provide the radar into the Gripen platform and the Typhoon. We also provide a number of surveillance radars, such as Seaspray and Osprey, to about 35 different customers across the world now, from US Coast Guard to a number of suppliers in Europe and Far East. We are also part of the Tempest GCAP programme, so that's the Global Combat Air Programme with Tri-Nation, with Italy and Japan. So we are the non-kinetic effector lead on Tempest GCAP. And I guess more importantly, the products that we have leveraged to work inside laser-directed energy weapons, we provide airborne lasers for a number of airborne platforms. We, who was talking about directed infrared countermeasures? We are the world leader of pointer tracker systems for directed infrared countermeasures. And we've combined that pointing and tracking capability we have with the ability to deal with high peak powers, peak power densities, and optics to work in laser directed energy weapons for the last 6 or 7 years. And I'll go into that in a bit more detail. So a little bit noddy, but just to make sure we're all talking about the same thing, I have a cartoon here just to show what an LG system is. So as Pooh said, essentially, these tend to be made up as a combination of individual laser sources. So in this cartoon here, we have fiber amplifiers. So typically an LG system may be made up of anything between 3 to 60 of these fiber amplifiers, combined either using spectral combination or coherent combination techniques, which Pooh was talking about. So what they do is essentially put an intense focused spot of light on the target. This heating can cause thermal damage at the surface or within the threat. It could cause thermal runaway. It could cause some kind of aerodynamic fault within the product. So that's essentially what it's trying to do. The fact that it's optical targeting enables very precise engagement, and also it does offer the benefit of potential minimised collateral damage as well. So essentially, large power and coolant. These tend to be wall plug efficiency of an LG system is about 30 to 33%. So if we're talking about a 50 kilowatt system, you're going to need about 150 kilowatts of platform power to actually run that system. So essentially, power and coolant coming in. We have a small milliwatt seed and fan out laser, goes into each of the fiber amplifiers, which then amplify up from milliwatts up to something in the range of 1 to 2 kilowatts. These are then combined using a coherent or spectral beam combiner. We have some diagnostics, and essentially their output through some kind of beam director or beam control system. LG has been around for a number of years now, but it's never quite made it into service, but it does offer a number of advantages over traditional kinetic effectors. There are logistical advantages. you essentially have an infinite or deep magazine. It is low cost per shot. It is logistically friendly. You know, deep magazine, essentially, as long as you have electrical power, you can fire the LG system. You do not require bullets. You do not require a logistical supply chain to provide those bullets. Low cost per shot. Typically, we talk about maybe 10 UK pounds per shot. So, as you can see, once you've paid for the NRE, the recurring cost of using the system, the logistical cost is low. And logistically friendly, you're not moving large munitions about the battlefield, so it's logistically less burdensome. Operationally, it has some benefits over kinetics. You can graduate your effect, you can deny, degrade temporarily, you can disrupt, you can destroy permanently the threat. You have the ability to operate covertly as a covert system. The light is invisible to the naked eye. It is agile. It provides very accurate targeting and tracking. So even if you're not using a laser for an LG system, it will probably provide one of the best electro-optical EOIR systems on the platform that it's there to protect. And also you have the ability to engage multiple targets in quick sequence. A key message that I like to get across to people when I talk about LG, though, is that it's not looking to replace kinetic platform protection. It is there to complement that and essentially offer a layered self-defense system. And LG systems are there. The W within it is a bit misleading. It is really there as a platform self-protection capability. What I've put on this slide here is really just a sample of some of the LG developments that are ongoing across the world. There are many. I couldn't fit them all in one slide. This is not exhaustive in any way, shape or form, but it just gives you a sample of what's going on at this point in time. In the US at the moment, they have a number of programs ongoing. They have a DAM SHORAD program. Companies such as Raytheon and Enlight have been active in that for a number of years. They have installed 50 kilowatt systems onto Striker platforms. These are land systems, and these have been deployed in the Middle East as a self-protection capability. They've also fielded for trials and operator interaction 60 kilowatt Helios systems with an optical dazzler onto various maritime platforms. And I guess interestingly, the US, if we want to talk about power scaling, they have a thing called the High Energy Laser Scaling Initiative. So this initially looked at moving from 100 to 300 to 500 kilowatts. And now that program is actually looking at 1 megawatt systems. These are more looking at how you would power scale and the challenges that that may bring as opposed to fielded systems. But they may have some form of static GBAD capability in the future. Germany has a number of ongoing developments in this area, 2 20 kilowatt demonstrators, namely Jupiter, Land and Howissam for maritime. Canada has been assessing high energy lasers for counter IED and counter UAV in the Army context, and also from a Navy perspective, UAVs and fast incoming attack crafts as well. The Netherlands, through TNO and LNR, have been looking, spending a lot of money in this S&T in this area for a long time, looking to transition to capability demonstrators. I haven't mentioned it here. There is an EADS, a European program called TALOS, that is looking at a sort of pan-European development program as well. And Australia has been very active in LG for a number of years, spending S&T, looking at next generation HEL demonstrators, and EOS, a specific company in Australia, has demonstrated a 30 kilowatt laser weapon station as well. In the UK, closer to home for myself, I'm heavily involved in the UK Dragonfire programme, which has been looking to build and demonstrate a 50 kilowatt prototype HEL technology demonstrator for the last 4 or 5 years. Recently announced by the UK government, there is the next phase of Dragonfire. This is termed the Accelerated Programme. So that is looking to put the Dragonfire system into service on UK maritime platforms by 2027. And also there are other R&D and TDP programmes running in the UK, led by a pan-mod team termed Team HERSA. So that is looking, that has projects running such as Project Swinton, looking at LG in the land sphere, and also Project Ealing, looking at an RFQ land capability as well. So some pictures here of Dragonfire, Swinton and Ealing. So these are no longer concepts on a page. These are essentially built pieces of kit that are being tested at this moment in time. So the LG systems are attractive because they have applicability across the complete mission spectrum. So here I've just tried to capture your legacy platform protection systems such as Phalanx, Iron Dome, Brimstone, Patriot, and where they might have effectivity. You know, DIRCM systems should probably be sitting in here as well. And then the example missions that they might look to take on: counter sniper, man pads, micro UASs, all the way through to large UAS and essentially cruise missile type things. So this just gives an idea of the kilowatt levels that the effectivity modelling that's been done across the world at the moment suggests that you would need in order to defeat these threats. So you have your small dazzlers down at your 1 watts, you know, the aircraft DIRCM systems, the single digit watts that Pooh was talking about, that Cailabs help out with, all the way up to the tens and the hundreds of kilowatts that LG systems are looking at to tackle this threat set. The technology that is employed across a lot of these LG systems at the moment is varied. Solid state lasers play a part, and direct diode. Solid state lasers, you know, essentially play a part even within fiber lasers as the erbium fiber, at maybe 976, something like that. But essentially, we have a whole range of EO technologies here that cover the spectrum of output energies that LG systems will be tasked with addressing. A little bit more about the Dragonfire capability demonstrator that we're involved in the UK. So we are part of a consortium with MBD and Kinetic. So we've been developing and demonstrating UK LGO capabilities for a number of years now. The Workshare MBD are the prime. They are providing the command and control of the platform and cooling. Our friends in Kinetic are providing the laser source, and Leonardo in Edinburgh are providing the beam director. So some images here. This is an image of a trial in the Outer Hebrides in the north of the UK last year. And this is a sort of cartoon showing the inside of the beam director, just a sort of Crowe representation. And another image of the trial, just you can see the laser system penetrating cloud at that Hebrides trial last November, December. Just to give you an idea of the context of the beam director that we provided, of which we've built 2 of so far. It's a highly precise and complex EO system. We have about 597 custom metal precision parts within it. We have 209 custom cable assemblies, 142 custom optical parts. There are 27 electronics units, 8 of which are bespoke designs, not COTS. We have 23 embedded software and firmware applications running at any one time. There are 18 precision motorized mechanisms within the beam director. We have 9 embedded processors, 7 cameras, and 6 different lasers operating within the beam director, and that doesn't include the high energy laser system itself. So this has been trialled extensively over the last 3 or 4 years. We have ran multiple non-firing target tracking trials, essentially demonstrating the sort of closed loop aim point tracking that we can provide with the system. So we've demonstrated that we can hold the beam onto something the size of a £1 coin or a €1 coin at ranges well in excess of 1 kilometre. And importantly, what we've done over the last few years is actually demonstrated the high power firing of the system as well. So a number of trials, extended land trial in 2022, but that was below the horizon. And more importantly, in 2023, images top and bottom here, these were essentially Europe's first above the horizon high power firing trial. So to fire above the horizon brings with it major logistical, safety and political issues. In order to do that, essentially we had to work with the US Laser Clearinghouse for satellite deconfliction windows. Some of the key photonics challenges that we have to address within LGO systems are, within the laser source, at the moment, a lot of these systems are reusing optical communications technology. So these are not really suitable for military environments or swap or ruggedization. Pooh was talking about photonic integrated circuits. That's one area where we see growth and S&T helping to reduce the swap and increase the ruggedization of LGO. The laser source also reuses fiber amplifiers and lasers that really are designed for material processing. So these lasers that we're using at the moment are mostly COTS, designed to work in a laboratory environment in controlled temperature conditions and without vibration. So these again are not suitable for what we're looking to do in the longer term, but a number of EO companies are looking to address this, including Leonardo. The beam director has provided a number of technical challenges also. We need extremely low jitter, that's essentially single digit microrads in order to achieve aim point control. We use high bandwidth, high quality FMMs in order to achieve that, and also to account for atmospheric perturbations as well. So these are operating at the 200-300 hertz rate in order to account for atmospheric irregularities that act on the beam. We have high-speed active imaging and tracking, so we're using gated illuminators and active cameras in order to give us good aimpoint control. The beam quality is obviously critical within the system. We need large laser path optics. We need low wavefront error. We need high efficiency optical coatings, and we're operating in multiple wavebands. As I said, there are 6 different laser sources within this system, all operating at different wavebands. We're controlling multiple sight lines, so we need to execute co-alignment to less than a millirad with parallax control. We need to align the sensor and the laser source to single-digit microrad. And one of the key things is that the HEL optics, the high energy laser optic path, need to be robust. So we need high laser damage threshold optics. We have a number of output window challenges that we need to resolve, and we need to manage the waste heat that's produced within an LG system. As I mentioned at the start, these are about 30 to 35% wall plug efficiency. So there's a lot of waste heat that has to be managed within the system. Last slide. So I guess a reach out to the optics industry. We really are looking for help. We're looking at S&T ourselves. We're looking at what other people are doing within the electro-optics industry to help us out. From optics, we're looking at novel coating designs that transmission, stress, LDT, multispectral capability, and environmental robustness are key to us going forward. We are looking for a reliable supply of large laser path optics. These essentially are astronomical size telescopes that we're talking about now. These aren't manufactured in large volume, but that's where we're going to have to get to. Coatings, we need to improve the LDT values of them. We need high peak power nanosecond pulse and high power continuous wave capable coatings. We are looking at complex items such as freeform optics and telescopes that provide collimation, direct view versus indirect view, and large scale, as I mentioned. Imaging, we need durable broadband external window coatings for all military environments. We need high precision zoom systems. Active components are incredibly important. We're looking for next generation detectors and a bunch of wavebands, visible SWIR. As I said, we have active illumination systems, so that needs active cameras as well as passive. We're looking at the advancements to help coherent beam combination. The Dragonfire system is a 50 kilowatt coherently combined system. And fiber lasers and components, we're looking for high rate, high power short pulse illuminator lasers, glassware such as pump combiners, optical isolators, and novel gain fibers. And lastly, supplier capability. We're looking for people that can provide these things reliably and at rate as well. That's really going to be very important in the future of LG. And I think that was it for me. So I'll hand you back to Mark.
Thank you very much, Kenny. That was a really interesting and fascinating overview of the kind of the wider context, and a clear call out for kind of collaboration, which is one of the purposes of these webcasts. Really, is to try and create as much communication between different companies and different sort of R&D solutions and things. Okay, well, we are nearly out of time, but we've probably got time for a few questions that have come in. One which was particularly came out of the Cailabs presentation, was a question about turbulence monitoring. How fast is the turbulence monitoring? Pugh, are you able to answer that for us?
Sure. So the turbulence monitoring, basically the limitation for us is the speed of the active recombination that we do with the Photonics chip. So these are kind of basically for phase modulators that are included in the Photonics chip. They can be actually incredibly fast. So today, the system we have include modulators that have a bandwidth of more than 10 kilohertz. So our system is able to compensate for turbulence up to 10 kilohertz. So this is much faster than what you can do with mechanical systems such as a deformable mirror.
Thank you for that. Another question that came in, which is a general one, I think, to the panel, for those that are in this space. What are your plans for laser cannons with upgraded output and range for DRAM defense? I don't know who'd like to go with that one first.
I could take that one if you like, Matt.
Sounds like you. Yeah, thank you.
Yeah. So I think one of the slides I put up did show that, you know, LGU will have capability across the whole mission spectrum, and CRAM is definitely one of the things that LGU is looking at as a threat. So CRAM is definitely something that LGU will be, it's in its key threat set, and is something that the first generation systems are looking to defeat.
Okay, thank you. And there was a question for Liquid Instruments here about the difference between the phase meter and the lock-in amplifier. When would you use one versus the other? Jason, are you able to answer that one for us?
So we have two solutions for measuring phase. Yeah, there's the lock-in amplifier and the phase meter, which are both available on the MOCU platform. So the idea is that the phase meter is better and more accurate if you have a strong signal to be able to lock onto, whereas the lock-in amplifier has a broader range and does better with signals that are closer to the noise floor or with intermittent signals. So both of these can be used to extract phase information. But yeah, the phase meter is generally better if you require higher precision, but you also have something to lock onto.
Thank you. And just while I've got you, is there a way, and this is a question, is there a way I can evaluate the MOCU software? How would people be able to do that?
Yeah, so we do have, if you can go to our website, and we do have a demo mode. So the idea is you can download the MOCU app and you can run it without owning any hardware. We just have, demo, just kind of data that you can take a look at. You can play around with the configurations and the connections, and you can do that on the demo mode of our software.
Okay. Thank you very much. Okay, we are just over time, so I think we probably should pause there. So that will bring us to very nearly the end of the today's webcast. Obviously, the webcast will remain live on the Electro-Optics website for up to 12 months. So you just need to go to www.electrooptics.com and download that. So if you've enjoyed the presentation, please spread the word to friends and colleagues, and they will be able to download it themselves to have a look. Thank you once again to our three speakers, so Jason, Pooh, and Kenny. It's been really interesting. We've had some good feedback on this already. Also to the Europa Science production team who are working hard in the background, and obviously to you for logging in today if you're watching this live or indeed have downloaded it at some point over the next few months. Please keep an eye out for future webcasts. We're always keen to have ideas for them. We've got some great ideas coming up. And so thank you very much. Thank you for your time. It is really appreciated, and hope to see you again sometime in the near future. Thank you. Bye-bye all.